Alright, so today is lecture number 10 and we're going to look today at a Fourier description of diffraction. So there was a homework problem in which we first of all tried to see that the Fourier transform of the direct lattice is the reciprocal lattice. Just to give you an example in 1D, if I have a train of impulse functions in a 1D lattice points are separated by some distance a, which is a period of the crystal, and the function can be written as a train of Dirac delta functions, right? So this is in 1D. The Fourier transform of this, the reciprocal lattice, we do know is also going to be a one-dimensional train of lattice points with a separation of 2 pi over a. So if I were to take a Fourier transform of this object of x minus n a, I apply the definition for the Fourier transform, which means I take the function, I multiply this with an exponential factor I k x, and I integrate over all of space. This is how we can define the Fourier transform. And it turns out that this is equal to E minus I k n a where n goes from n has all positive and negative integers in it. So it's an infinite sum of exponential functions. Now we can show that this infinite sum of exponential functions is really equal to a train of impulse functions, right? So what we could do is we could take this function and express it as a Fourier series. ठीक है? So किसी ने ये सवाल किया था ये होमवर्क के अंदर है इस वक्त आपके पास? Two pi over a k minus n 2 pi over a. So this sum of exponential functions is actually equal to a sum of Dirac delta functions. So what we need to do, so if you look at the full derivation for this, it's pretty simple. So if I take any functions x minus n a, is this periodic? Is it periodic? It is periodic, so it can be written as a Fourier sum. Let that Fourier sum be equal to some CP, some Fourier coefficient E plus I k x, some p x over the period a, sum over p. Okay, so this is the Fourier series. Now we need to determine the p's, and I think there's a 2 pi here as well. So the p's, Cp is the Fourier coefficient, is given by this function x minus na e minus I p x over a, and you integrate this over x over a period. Now a period extends from minus a by 2 to plus a by 2. That's the length of one period. And you divide by the period as well, which is 1 over a. Now this function delta x minus na samples this function, which means that x equals na. X has to be equal to na. So this becomes minus ipn, and you're taking a sum over all n's. Okay, so yes please. Okay, so this is the Fourier series. Okay. This periodic function in space is written in this form. This is a Fourier coefficient. This Fourier coefficient can be determined by this formula. Okay. The Fourier coefficient is determined by this Fourier integral. Now the Fourier integral, let's compute this Fourier integral. CP equals 1 over a sum over n dx. X goes from minus a by 2 to plus a by 2. Now look at the limits of this integration, minus a by 2 to plus a by 2. So the only value of x for which this integrand is non-zero is x equals 0 in this limit. So if I put x equals 0 here, this turns out to be 1. So all of this is now equal to 1 over a. What this means is that my CP is equal to 1 over a, which means that this train of Dirac delta functions over all n's in 1D is really equal to 1 over 2 pi a ei p x over a. Okay, this true? This is true. So what I just do sum, this is a sum over all p's. What I would like to do now is simply take, let's in this expression replace x by k. K minus na 2 pi a p ei p k over a. Okay. Now I can put a minus sign here if I like, because it is sum over all p's. So this is really plus minus. I can put a minus sign here by choice as well. Okay. Now what I need to do is I replace a by, let's replace a by 1 over a. Right? So if I do that replacement, or let's replace a by 2 pi over a. Okay, if I were to make this replacement, ये तो 2 पाई का फैक्टर एक मैंने कहीं एक मिनट There's a 2 pi here as well in the Fourier series, right? So, okay. So there's a 2 pi here as well, 2 pi. So I replace A by 2 pi over A. This becomes E plus I pKa. Okay, P. This becomes 2A is to be replaced by ये भी 1 over 2 pi मैंने गलत लिखा है, ये नहीं है, सॉरी, फोरियर सीरीज में नहीं है. So now A is replaced by A over 2 pi. This becomes N delta K minus NA, right? Correct? Now what this means is that this sum, I can put a minus sign here as well, can't I? Because it's sum over all p's. So this means that my sum over E minus I K, now I can replace this P with, since it's the sum over all integers, this sum over all integers, I can have the same, I can replace this P with an N, doesn't matter. So this means minus I K NA is equal to 2 pi over A. This is 2 pi over A because I made this substitution. K minus N 2 pi over A. Correct? All fine? So this sum over exponents, which is the Fourier transform of another train of Dirac delta functions, is another train of Dirac delta functions in which the spacing between two successive points is 2 pi over A. So when I start off with a direct lattice, which is just a sequence of points periodically spaced, I get another sequence of points periodically spaced which has a reciprocal spacing between the points, which is the reciprocal lattice. Any questions about this? So this means that the Fourier transform of my lattice, and I represent Fourier transforms by this double-sided arrow, is 2 pi over A. It's an inconsequential coefficient K minus N 2 pi over A. So if this one-dimensional lattice is a part of a three-dimensional lattice, then this sequence of points in 1D spacing A, if I take its Fourier transform, I will get a plane, sequence of planes in the other two dimensions. Correct? So this is a sequence of planes like this. Right? This is, you can say, the kx axis, and this spacing is 2 pi over A. Correct? Now how do you create a three-dimensional lattice? You create a three-dimensional lattice by taking a row of points and convolving it with another row of points in a perpendicular direction. Correct? So if I take this row of points along x and then I take a Dirac function delta y minus NA, which means I'm taking this row of points and convolving it with another row of points in a perpendicular direction, then the Fourier transform of this will also be another sequence of points, planes, which are now two-dimensional but in an opposite direction. Right? Okay, since I'm talking about, say, a primitive cubic lattice, all of these lattice spacings, suppose I'm talking about an orthogonal lattice. So if this is B here, then this spacing between planes is 2 pi over B. Okay? The reciprocal lattice vector in this case is A star, which is perpendicular to the B and C directions. It's along A, and it has a magnitude of 2 pi over A. Right? Here, the unit vector, the unit translation vector in the reciprocal space is B star. Correct? So now if I do the third dimension, which means a plane of points coming out, this will also create another plane of points in the reciprocal space. Correct? Now if I've taken convolution in these 3 dimensions to create a 3-dimensional network of lattice points. So this is one net. Here is another net at the back, another net at the back. So I create a 3-dimensional network of points. Then the Fourier transform of this lattice will just be the product of these planes. And what will the product of these planes look like? It will be a sequence of points. Okay, so if I take the product of these lattice points, I'll get, so when I take the product of this and this, I'll get rows in parallel rows like this. This is one plane, other plane, another net. Right? So then I kind of striate this along the third dimension and get a sequence of points. Okay? So the reciprocal lattice has been generated. So the reciprocal lattice is just a Fourier transform of the direct lattice, and this is a direct bearing on diffraction theory. So if I take, by extension, if I take a 3-dimensional lattice, 3-dimensional direct delta function R minus some Rn, where Rn's are the translation vectors along A, B, C, and I take the sum over all n's. Now this n is really a tuple of points. It has 3 integers, n1, n2, n3. So this n really means n1, n2, n3, and I take this sum, which is a representation of my direct lattice. Then its Fourier transform will likewise be 2 pi cube over the volume of a unit cell in the direct space A dot B cross C, and a 3-dimensional network of points given by K minus the G vectors, the reciprocal lattice vectors, which are identified by the planes H, K, L. Okay, so I sum over H, K and L's. So this is the reciprocal lattice. Okay. So each G is H A star plus B, K B star plus, so each of my G vectors, reciprocal lattice vectors, is a translation vector in the reciprocal space given by H A star plus K B star plus L C star. Alright. Now what we would like to do is, if you look at the crystal itself not only has a lattice, so this is my lattice LR, but at each lattice point you put a basis. So this is really the convolution of the lattice and the basis. So there is some distribution that is associated with the basis that you put on each lattice point. This is the entire crystal structure, and if I were to take the Fourier transform of all of this, I need to find the Fourier transform of the basis, which we'll do today in the class. So, but all in all, the convolution theorem states then that this Fourier transform of the crystal, the entire crystal itself, is given by the product of this thing, HKL K minus G HKL, and you multiply this with the basis transform of the basis, which is B K. So I just put these double carets on top of it so that this is in the Fourier domain. Take the Fourier transform of this. This is the Fourier transform of this. This is the Fourier transform of that, which is nothing but saying that B of K is B of R E minus I K dotted with R over all of space, three-dimensional integral. Okay. So what this really means is, if I look at this from a graphical perspective, if I have the reciprocal lattice points, is the train of Dirac functions. So I'm just drawing this in 1D. This is this function over here. The basis will have some Fourier transform. The basis is smaller than the size of the crystal, so it has a big, large Fourier transform. Suppose that Fourier transform is something like this, right? Then what this object is doing is it's sampling this Fourier transform at these precise points. So it's a simple multiplication. So this will result in some sequence of points. This will be CK, the Fourier transform of the entire crystal structure. All right. In fact, so the Fourier transform of the entire crystal structure is the motif Fourier transform sampled at the reciprocal lattice points. Now, another thing that you would like to mention is that whenever you see a spectrum, now I need to relate this to the diffraction spectrum that I haven't done at the moment, but so far so good. Another thing you might notice is that in diffraction patterns you never get Dirac delta functional peaks. There's some spread, so you get peaks of this kind. So this dispersion on each point, this width on each point, can come from different sources. One of the sources is that the crystal itself is of finite size. Okay. So if I look at this this lattice vector. This is bounded, it has surfaces.
सर ये वो गिब्स phenomenon से
अभी नहीं गिब्स phenomenon नहीं अभी convolution है सिर्फ, it's all about convolutions. This is one of the most beautiful examples of how Fourier transforms apply to real systems and to diffraction. So this is the crystal, but this assumes an infinitely sized crystal. It's very large, it has no surfaces, but overall everything is bounded. So what kind of mathematical function do I need to apply to bound this on its outer side, to put an upper limit on r's? I need some other shape function, which is like a step function, which is one, you know, unit step functions of this kind. So if I have some x, a function which is 1 and then suddenly drops to at some x naught drops to 0. Electrical engineers call this something of this kind, a unit step function. Correct? So I need some kind of shape function of this kind. So this entire crystal function CR, if I take into account the shape of this as well, is L of R convolved with B of R, and all of them is then multiplied with some shape function. And in the Fourier domain, this multiplication results in a convolution. Right? So if I have a shape function, so depending upon the size of the object, I'll get a shape function. Suppose I have a spherical particle, a spherical nanoparticle perhaps, its shape function will also be like a sphere, it will be spherically symmetric. Or I have a Gaussian shaped particle, its shape function will also be Gaussian shaped. So the Fourier transform of this will, suppose it looks like this. Now convolution means that you have a sequence of points, you convolve this shape function with this sequence of points, you'll get this shape function replicated on all the Dirac delta functions. Right? So this is your final Fourier transform of the finite sized crystal. And this is actually related to the diffraction pattern. If you take the modulus square of this diffraction pattern, you'll get the distribution of intensities from X-rays, as we're going to see in a minute. So any questions about this Fourier description? You have smaller particles. So if you do diffraction studies of nanoparticles, smaller sized particles, to the point that you get that each nanoparticle becomes a single crystal itself. That's the ultimate limit. Each small nanoparticle becomes a single crystal itself. Then its shape function in the Fourier domain will be very big. So you will get wider peaks, less sharp peaks for smaller size crystallites. Okay, if you have a big crystal, a lot of crystallinity near, no grain boundaries, you'll get very sharp peaks. So smaller size nanoparticle X-ray diffraction gives you broader peaks. To the extent that for an amorphous material, which does not show any crystallinity, you just get a broad bump. No peaks are seen. For liquids, you can do X-ray diffraction for liquids as well. So this is the Fourier description of the lattice and the structure. Now let's move on to diffraction and relate this to diffraction itself. Now I would like to start off by electromagnetic radiation, correct? But when you have a detector for X-rays, what is it measuring? Physically, it measures some property of the radiation. What is it measuring? What do X-ray detectors or any detectors measure when they look at electromagnetic fields? In the lab, you work with optical detectors. What do they measure? They measure intensities. They don't measure fields. They measure intensities, which are the modulus square of the electric field associated with the electromagnetic wave. So far what we've done in our previous classes is that when we were looking at X-ray diffraction, we saw at what thetas do the peaks lie, right? But we do not tell what is the intensity of each peak. So now, with the help of this formalism, we can tell what is the intensity of each peak. And it turns out that since we're measuring intensities, if we take this crystal structure and take the modulus square of this, that will be proportional to the intensity of the peak for a given HKL. So since this sum is over all HKLs, this gives us the total, the modulus square of this will give us the total intensity coming from that crystal. But if we suppress this HKL for a given HKL, if we just don't take the sum and set the values of HKL, we can find the intensity due to a reflection coming from an HKL plane. Right? That's what we want to do at the moment. So first of all, let's call all of this F. And it's a function of K. Now don't confuse this K vector. This is a reciprocal lattice vector with this index, Miller index K. The context will tell you what I'm going to talking about. So this is 2 pi cube over the volume of the unit cell, sum over HKL K minus GHKL BK. Okay, so for a particular HKL, let's now look at this function F. This function F is called the structure factor. Structure factor. This function, let's compute this for a particular value of HKL, which means I suppress this sum. So F for some HKL, still a function of K, is 2 pi cube P this unit K minus GHKL, where this K, H and L are fixed by what do we want to find? Which HKL, which reflection are we looking at? BK. Okay, so far so good. Now this BK is a Fourier transform of the distribution of charge in a motif, because X-rays are interacting with the electrons inside the atoms. Okay, because the electron cloud, when it sees the electric field of the X-ray, it accelerates and rescatters radiation which is being detected. So it's scattering of radiation which is being detected. And the Bragg viewpoint of reflection from planes is a useful construct which is analogous to the scattering process, which completely describes the scattering process. Okay, that's what we do know. So it's really a scattering of radiation that is taking place. So there's a scattering problem that we're trying to look at. So this BK is, if I assume that this is my distribution of charge, rho r, it's distributed in space, then I take the Fourier transform of this, I will get B. So what is my FHKL, the structure factor? FHKL, and by the way, do keep at the back of your mind that the intensity of a peak IHKL is proportional to, up to some factor, I mean, we have all kinds of factors that will come in, is proportional to FHKL mod squared. Okay, so this FHKL is now given by 2 pi cube over V d cube R K minus G HKL rho R E minus I K correct. Now this samples the values of K's, right? So you apply the sampling theorem and you will get 2 pi cube over V T cube R rho R E minus I G H K L R. Correct? Now let's assume some form for rho R. Okay? So far so good. So I've just replaced this K with GHKL. Alright. So now if I look at my crystal structure and I see how electric charge is distributed, of course I have a lattice. So let me draw a few unit cells. So this is my origin for R. So I need to define an origin for R for the position vector. Suppose this is my position vector for R. It's a three-dimensional space. So and I take a point in the neighboring unit cell. And then there is, so I take this point in the neighboring unit cell, which is 2 units away along A, 1 unit along B, 1 unit along C and so on. So it's in a neighboring, it could be in any unit cell, any lattice point. So on this lattice point I've put a basis. So suppose I take this lattice point and I put a basis of atoms, right? Some arrangement of atoms on this point. This basis will exist on each of these lattice points. So now this is a discharge, some charge here, some distribution of charge here, some distribution of charge here, some distribution of charge here. Correct? And it needs 2 kinds of indices. One, how far away am I from the origin? Where is this lattice point? In which unit cell? How many translation vectors do I need to move from here to here, from here to here? And when I reach that lattice point, where is the basis? So my rho R, a good kind of model for rho R is that this equals some 3-dimensional function where R is given by R n, where n is a tuple of points showing where are we in the direct lattice, which unit cell are we at, n1, n2, n3, plus the atomic coordinates, where is that basis, where is that atom inside the motif. So this small vectors, these are the RAs, and this vector is an Rn. So this is a distribution of points, okay? And you sum over all n's and all a's, which I'm now putting as vectors, right? Because there are tuple of points. And then there is some factor. Since now I'm going to talk about diffraction, there is some factor that is associated with the interaction of radiation with electrons itself. This can also have some dependence on theta. There is some scattering factor that needs to be taken into account. Okay, so I put some scattering, atomic scattering factor here. So these are the pinpointed locations of the atoms, but associated with each atom there has to be some coefficient as well, which tells you kind of the amount of radiation that can be scattered from a carbon atom, from a cesium atom, from a sodium atom. They will have different scattering factors, different interactions with the X-ray radiation. So that has to be quantified as well. So this Fa is called the atomic scattering factor. Yes. And then if you have some electron itself, so this is the distribution of the electronic cloud. Fa tells you the distribution of the electronic cloud. Comes from the wave function of the electrons inside that atom, as we will see in a minute. Okay, so this is our rho r, the distribution of electronic density inside this material, which is rescattering radiation. Now I need to put that rho over in there, right? Let's put that function for rho into that structure factor FHKL. Okay? Two pi cube. Now this is a kind of inconvenient legacy, but never mind. D cube R or NA FA E Okay, so if I break this down, now what I need to do is, this is an integral over space. I can break this integral over space, since each unit cell is identical. I can break this integral over space into, it's a multiple of each unit cell, and you multiply this with the number of unit cells, correct? So if I take a number of unit cells to be n, then I can replace this integral over all of volume to integral over a unit cell. Okay? And then look, R is bounded at Rn and Ra. So this R can take up values of Rn plus Ra only, otherwise it's 0. So I can now break this up into Na, Fa, E minus I, GH, KL, Ra, correct?
n की वजह से डायरेक्ट रेट ऑफ फंक्शन क्या है?
सॉरी,
n की वजह से डायरेक्ट रेट ऑफ फंक्शन हमने रिमूव किया या
नहीं ये तो हमने सैम्पलिंग थ्योरम की वजह से किया, ठीक है। एंड आई टेक द सम ओवर a, take the sum over n, and this applies to a unit cell only. So this integral really can be taken over here. This integral sign can be shifted over here. So now let's look at this fact. Let's look at this expression. This is an expression for f h k l. Really nice, really important, and I think this is a beautiful result. What we see is that this structure factor is a product of two structure factors. One is due to the lattice. This is purely due to the lattice because there is only n. So this n, by the way, now is, since I'm taking an integral over the unit cell, let me just clarify a few things. Let me write this down again. Both of them are, so that big structure factor is a product of two structure factors. Let me write this down. FHKL is 2 pi q over v, number of unit cells, sum over a is all the atoms inside the basis. F of a e minus I g h k l, the position of the basis vector which has the lattice, corresponding lattice point inside the unit cell as its origin, because RA is measured from the lattice point. So this is for all the atoms inside the basis. This is one kind of structure factor. This is the structure factor, let's call it SHKL, due to the basis. Okay, and you multiply this with E, this was minus I GHKL over R M. Now this, when I took the applied the sampling theorem here, this R is replaced by Rn and Ra, then actually this integral also goes away. Right? With the caveat that this n is inside a unit cell. Only inside a unit cell. Correct? Since I'm taking overall space, I focused on a unit cell. That's why I put an n here. So now I'm just looking at a unit cell. Now in a unit cell, there is this Dirac delta function which is only sampling points at the lattice points. Which is only sampling the function, this exponential function at the lattice points. So if I were to take all the lattice points inside a unit cell, then it's enough. Alright? So for a primitive, there is only one point in a lattice cell. For a body centered, there are two. For a face centered, there are four. For a base centered, there are two. So you just have 1, 2, 3 or 1, 2 or 4 points to be considered for different kinds of Bravais lattices. So this is due to the lattice. This factor is due to the lattice. This is n inside the unit cell. So this is due to the lattice solely. Okay. So this is our structure factor for this crystalline structure. It's a product of two structure factors. One is due to the basis and one is due to the lattice itself. Now, one further kind of really neat thing, if you look at the lattice, this Rn, inside the lattice, this Rn is defined by some say x a plus y b plus zc. For primitive x, y and z are always 0. Correct? So this factor for a primitive unit cell, let's talk about SHKL for a lattice. For a primitive, this is 1. For a primitive Bravais lattice. For a body centered, this is going to be, since x is half, y is half, z is half, that's the second point belonging to that unit cell. So there are 2 points in the unit cell, one at the origin and one at the body center. So this factor is going to be 1 plus E minus I. GHKL, as you all know, is H A star plus K B star plus L C star. Correct? So if I take this GHKL and I put half here, I will be left with minus 2 pi over 2 H plus K plus L. So this is the structure factor for the lattice for body centered. Sorry. ठीक है? Minus I pi into HK plus L. So the structure factor to lattice for primitive is this one, just 1. For body centered it's this. For face centered it will be 1 plus E minus I. Remember that A dotted with A star is 2 pi. A dotted with B star is 0. A dotted with C star is 0. Okay. So for face centered it's going to be 1 minus 2 pi over 2 H plus K plus 1 minus I pi H plus L plus 1 minus I pi K plus L. This is for face centered. And you can also find it for any base centered. So for body centered, if this factor is 0 unless H plus KL is even. So the structure factor disappears unless HK plus K plus L is an even number. That's what we've seen in our previous lectures as well, that for a body centered direct lattice, the diffraction pattern, the peaks only exist when H plus K plus L is even. And this comes out from the structure factor. No matter what the basis structure factor is, the lattice determines, kind of puts on certain constraints on the reflection. This factor is 0 unless unless all the indices are even or all the indices are odd. So for a face-centered cubic system, the reflection is 0, does not exist unless all the Miller indices from which a reflection is coming are even or they're odd. Okay, so this helps us determine the structure factor for the entire crystal, which is partly kind of coming out from the lattice. And then if this is non-zero, then one has to move to calculating what the structure factor for the basis is. Probably we're going to spend one more class on this because we have short time. Any questions about this? Yes? फेस सेंटर्ड के लिए जो x y और z है ना वो ये होते हैं 0 0 0 0 हाफ 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 0 हाफ और हाफ हाफ 0। तो इसको अगर आप यहाँ डालें ना, इस इन आर एन्स को इसके साथ मल्टीप्लाई करें और एक्सपोनेंट में डाल दें तो आपके पास ये टर्म्स आ जाएंगी। Okay, so now we've derived the structure factor for the crystal structure, which is a product of the structure factor for the lattice itself and the basis. The lattice imposes some constraints on the structure factor. Sometimes it turns out to be 0. No reflection can be seen in that case. Okay, but the Fourier theory is an absolutely brilliant theory which kind of connects all of these ideas together. All right, so let's continue this discussion and wrap it up on Tuesday.